Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at the structure of the cosmos, exploring how matter arranges itself from the smallest building blocks to the largest patterns known in the universe. The purpose of this story is to help you learn while resting, allowing your mind to follow simple scientific explanations that move at an even pace. If sleep does not come immediately, that is completely fine. You can still take in a few interesting details about the universe as you settle. Simply listen, let your breathing slow, and allow the information to settle at its own pace. If you would like to support the channel, you can like and subscribe, but there is no need to move or search for anything now. You can just remain as you are while we begin. When we talk about the structure of the cosmos, we are describing the way matter organizes itself across a wide range of scales. These scales span from the tiniest particles to immense systems of galaxies that stretch across hundreds of millions of light years. Even though the universe appears vast and open, its contents are not scattered at random. Instead, they follow consistent physical principles that shape the patterns we observe. These principles operate quietly, without interruption, producing an ordered arrangement that has developed over billions of years. The cosmos begins with fundamental elements that are far smaller than anything we can see. Particles such as electrons and quarks form the foundation of atoms, and atoms form the basis of all matter. These particles behave according to stable laws that have remained unchanged for as long as the universe has existed. Because these laws hold firm, matter is able to assemble into recognizable structures. Without this stability, larger forms such as stars and galaxies could not develop. The regularity of particle behavior anchors every step in the construction of cosmic structure. From these smallest components, the universe builds upward. Atoms combine to form gases and molecules, which drift through space in vast clouds. Over time, these clouds respond to gravity, pulling together and increasing in density. As their centers grow hotter and denser, new processes begin that will eventually lead to the formation of stars. None of this happens quickly. The development of structure is measured in millions and often billions of years, which gives each step a quiet, gradual quality. As more complex forms arise, larger patterns become possible. Groups of stars form systems, and systems gather into galaxies. Each galaxy rotates, holds its stars in stable paths, and interacts with its surrounding environment. The physical laws that guide galaxies operate across tremendous distances, yet they remain as consistent as those that hold atoms together. Because of that, the cosmos has a layered architecture, with each scale building on the stability of the one before it. Even at the largest scales currently observable, matter displays a level of order that reflects these underlying rules. Galaxies do not drift alone but assemble into groups, clusters, filaments, and wide networks that stretch across a significant portion of the universe. These patterns appear intricate when mapped by telescopes, but they arise from simple and predictable relationships between matter, gravity, and time. The universe does not rush. It builds structure at a pace set by its own physical limits, allowing us to trace the steps that lead from early conditions to the complexity we observe today. In this episode, we will follow this path from the smallest scales to the greatest, observing how each layer contributes to the next. By understanding these connections, we can better appreciate how the cosmos maintains its quiet, orderly arrangement. There is no need to grasp every detail. You can simply listen as the structure reveals itself slowly and steadily, much like the universe itself has always done. To understand how the cosmos builds its larger structures, it helps to begin with the smallest components that make them possible. At the foundation of all matter are particles that cannot be seen directly. Particles such as electrons, quarks, and neutrinos behave in precise ways that have remained consistent across the entire history of the universe. Their interactions follow stable laws of physics, and this stability allows every layer of structure above them to form and persist. Without consistent particle behavior, atoms would not hold together, molecules would not form, and larger patterns such as stars or galaxies could never appear. These particles do not move freely without guidance. Their behavior is shaped by forces that act at very small scales. The electromagnetic force governs how electrons orbit atomic nuclei, creating the stable arrangements that allow atoms to behave predictably. The strong nuclear force binds quarks together into protons and neutrons, ensuring that atomic nuclei stay intact. The weak nuclear force allows certain forms of decay that play a role in stellar processes. Even gravity, which seems weak on these small scales, becomes essential when matter begins to gather in large quantities. Every structure that will appear later depends on these forces maintaining their predictable roles. Although these particles are incredibly small, their properties define the potential for all larger structures. Each particle carries specific characteristics such as mass, charge, and spin. These properties determine how particles interact, how they combine, and how they organize themselves into increasingly complex forms. The consistency of these characteristics across time allows matter throughout the cosmos to behave in similar ways, whether it lies within a star, a planet, a gas cloud, or a distant galaxy cluster. When particles come together, they form atoms. Hydrogen and helium atoms emerged first when the early universe cooled enough for electrons to settle into stable orbits around nuclei. These atoms were simple, but their stability allowed matter to exist in a form that could later gather into clouds, stars, and galaxies. Even at this early stage, the fundamental structure of matter was already taking shape. The universe had moved from a hot, uniform state toward one capable of building complexity. Atoms themselves behave predictably because their internal structure is governed by quantum mechanics. Electrons can occupy only certain energy levels, and these levels determine how atoms interact with one another. When atoms share or exchange electrons, they form molecules. Molecular bonds represent the first steps toward organized matter at scales larger than single atoms. Although simple compared to the structures that will form later, these bonds rely on the same precise and unchanging laws that have guided particles since the earliest moments of the universe. As atoms and molecules drift through space, they are influenced by gravity. Gravity acts on every form of mass, regardless of size. While its effects on individual particles are minimal, its influence becomes significant when matter collects in large quantities. Over long periods, gravity draws atoms toward one another, gradually increasing the density of gas clouds. These clouds become the seeds of stars, galaxies, and even larger formations. Without the predictable behavior of particles and forces at the smallest scales, gravity would not have stable material to shape into larger patterns. The smallest structures in the universe may be invisible to the eye, yet they carry within them the instructions for every larger form that follows. Their reliability provides a foundation on which the cosmos builds layer after layer of organization. We will move from these microscopic foundations to the behavior of atoms as complete units, showing how their stability and interactions enable the universe to progress toward more elaborate and visible forms of structure. Atoms represent the first level of structure that moves beyond the behavior of individual particles. Each atom has a nucleus made of protons and neutrons, with electrons arranged around it in stable configurations. These configurations arise from quantum rules that determine which energy levels electrons can occupy. Because these levels are fixed and consistent, atoms behave in predictable ways, and this predictability makes larger structures possible. Hydrogen and helium formed first, becoming the foundation for almost all the matter that later gathered into stars and galaxies. The stability of atoms is essential for the development of structure in the universe. A hydrogen atom retains its shape because the electromagnetic attraction between its positively charged nucleus and negatively charged electron is balanced by the motion of the electron itself. This balance does not vary across space or time. Wherever hydrogen exists in the cosmos, it follows the same principles. This consistency allows matter to assemble into coherent forms, whether inside a star, drifting through interstellar space, or part of a distant nebula. As atoms combine and separate, they create the dynamic environment necessary for the next stage of cosmic structure. When atoms share electrons, they form molecules. When they collide under the right conditions, they can break apart or exchange energy. These interactions occur in clouds of gas that occupy large regions of space. Within these clouds, Atoms and molecules are not arranged in uniform patterns. Instead, they drift, collide, and respond to slight variations in temperature, pressure, and density. These variations create conditions that gravity can act upon, drawing matter slowly toward regions where density becomes greater over time. The universe's earliest gas clouds were vast, stretching across distances that appear almost unimaginable. Within these clouds, slight irregularities became important. Where density rose slightly, gravity increased its pull on nearby matter, causing more gas to accumulate. Over long periods, these clouds began to contract. As they did, atoms were brought closer together, collisions increased, and temperatures rose. This process would eventually lead to the birth of stars, but its foundation lies entirely in the behavior of atoms and their ability to interact in stable and consistent ways. The early universe contained mostly hydrogen and helium because heavier elements did not exist at that time. Those heavier elements would be created later in the cores of stars, but the first generation of stars formed from these simple atomic building blocks. Their emergence depended on the ability of atoms to cool, combine, and compress within large clouds. Cooling is an important step because it allows a cloud to contract under gravity rather than expanding outward. Atoms radiate energy as they collide and change states, allowing the temperature of a cloud to drop enough for gravity to continue its work. As atoms come together under gravity, the central regions of a collapsing cloud become denser and hotter. The structure of atoms dictates how they respond to these rising temperatures. At certain thresholds, conditions become sufficient for nuclear fusion to begin, and at that moment, a star is born. This transformation is dramatic on cosmic scales, but it arises entirely from the predictable behavior of atoms and the rules that govern their interactions. The stability of atomic structure ensures that these processes occur consistently throughout the universe, no matter where a cloud begins to collapse. Atoms remain the foundation for all later structure. Every star, planet, and molecule of interstellar dust depends on their reliability. Their consistent properties allow the universe to build layer upon layer of complexity. Understanding atoms helps us appreciate how the cosmos transitions from simplicity to the rich structures that fill space. We will follow these atomic foundations into the formation of stars, where gravity and temperature combine to create the first luminous structures in the universe. As atoms gathered into large clouds of gas, gravity became the guiding force that shaped the next major step in cosmic structure. These clouds drifted through space for long periods, sometimes remaining diffuse and quiet, and sometimes encountering conditions that allowed them to begin a slow collapse. Gravity acts everywhere, but its influence becomes noticeable only when enough mass collects in one region. In the early universe, large gas clouds served as the places where this gradual transformation began. Within them, hydrogen and helium atoms moved, collided, cooled, and responded to small differences in density that ultimately shaped their evolution. A collapsing cloud does not fall inward quickly. Instead, the process unfolds at a steady pace, determined by the amount of mass in the cloud and the ways its atoms release energy. As atoms move closer together, the temperature rises, and collisions become more frequent. These collisions allow atoms to radiate energy into surrounding space, which helps the cloud continue contracting rather than pushing outward. This balance between heating and cooling is essential. If the cloud cannot radiate enough energy, it will not collapse toward the densities needed for new structures to emerge. When cooling is effective, gravity guides the cloud toward a denser and more organized form. As the collapse continues, the central region of the cloud grows significantly hotter and more compressed than the outer regions. Here, atoms are packed so closely that their behavior changes. Temperatures climb to levels where atomic nuclei begin to interact in new ways. When conditions become extreme enough, nuclear fusion can begin. In fusion, hydrogen nuclei combine to form helium, releasing energy in the process. This energy is released as light and heat, creating the first source of sustained illumination in the universe. A star has formed. The birth of a star marks a significant threshold in cosmic structure. Before stars existed, the universe contained matter, but it had no internal sources of light. When the first stars ignited, they filled their surroundings with radiation, shaping the evolution of nearby gas and influencing the development of later structures. The fundamental behavior of atoms makes this possible. Fusion could not occur if atomic nuclei were unstable or if the forces that hold them together behaved unpredictably. The same laws that govern particles at the smallest scales now support the formation of these large and luminous objects. Once fusion begins, the new star stabilizes. The energy produced at its core creates an outward pressure that balances the inward pull of gravity. This balance allows a star to remain steady for millions or billions of years. Its temperature, brightness, and lifetime depend on its mass, but all stars follow the same general pattern of formation. Gravity compresses, temperature rises, fusion ignites, and equilibrium forms. The star becomes a structured system, with layers and behaviors determined entirely by the consistent laws of physics. Stars are the first major structures that reshape their environments. Their light warms surrounding gas, their stellar winds influence nearby regions, and their eventual deaths will return enriched material to space. The presence of stars marks the beginning of a universe filled with organized systems that build upon one another. Each star is both a product of earlier simplicity and a source of new possibilities. Without stars, galaxies would not take form, planets would not emerge, and heavier elements would not exist. The transition from gas cloud to star illustrates how the cosmos builds structure through predictable steps. Gravity gathers matter, temperature and pressure rise, new physical processes begin, and stable systems emerge. We will see how stars group together into galaxies, creating the larger formations that define much of the universe's visible architecture. As stars formed across the early universe, they did not remain isolated. Gravity continued to act over long distances, drawing stars together into larger and more organized systems. These systems became galaxies, the major structural units that shape much of the visible cosmos. A galaxy contains stars, gas, dust, and dark matter, arranged in patterns that reflect the interactions of gravity, rotation, and time. Although galaxies can differ in appearance, they all share the property of being stable structures built from countless smaller components. Most people are familiar with spiral galaxies, which display graceful, curved arms extending outward from a central region. These arms are not rigid structures, but areas where stars and gas are more concentrated. Spiral patterns arise because the rotation of the galaxy influences how matter moves through its disk. Regions of slightly higher density encourage star formation, and the presence of young, bright stars makes the arms more noticeable. Although the shape appears dramatic, it emerges naturally from the dynamics of large collections of matter responding to gravity. Elliptical galaxies present a different form. Instead of having distinct arms, they appear as smooth, rounded clouds of stars. Their shapes result from long histories of interactions, including mergers between smaller galaxies. When galaxies collide and eventually combine, their orbits and structures change, sometimes losing the organized rotation that produces spiral patterns. The outcome is a more uniform distribution of stars that blends into a rounded form. This process takes place over hundreds of millions or even billions of years, guided entirely by well-understood physical principles. Irregular galaxies do not have a defined shape. Their appearance often reflects recent gravitational interactions or internal activity that prevents them from settling into a stable, orderly structure. Even so, their stars and gas follow the same fundamental rules that shape every galaxy. Gravity binds them, internal motion organizes them, and their long-term evolution depends on the balance between these forces. At the center of many galaxies lies a dense region containing a large number of stars. In some cases, a massive black hole occupies the core. These black holes exert strong gravitational influence, affecting the motion of nearby stars and gas. Their presence helps define the internal structure of the galaxy, although they do not dominate the overall dynamics. The broader shape and behavior of a galaxy depend on the combined mass of all its components, including the matter that cannot be seen directly. Dark matter plays a central role in galaxy structure. Although it does not interact with light, it contributes most of the mass needed to hold galaxies together. Without dark matter, the visible material within a galaxy would move too quickly to remain bound. The presence of dark matter creates a gravitational envelope around the galaxy, helping to maintain its stability and shape. Astronomers detect its influence by observing how stars orbit within the galaxy and how light bends when passing near massive regions. Galaxies do not exist in isolation. They interact with their surroundings, exchange material with intergalactic space, and sometimes collide with neighboring systems. Over long periods, these interactions shape their evolution and influence their appearance. Despite these changes, galaxies stay connected to the broader structure of the universe. Their distribution across space forms patterns that extend far beyond individual systems. The emergence of galaxies marks a major step in the development of cosmic structure. They provide the framework for stars, planets, and many of the features we associate with the universe's visible form. Understanding galaxies helps us appreciate how matter organizes itself into coherent systems that endure across billions of years. W will expand our view to see how galaxies gather into clusters, revealing the next layer of structure in the cosmos. Galaxies, vast and complex on their own, do not float through space as solitary islands. Gravity links them across even greater distances, guiding them into groups, clusters, and larger associations that shape the architecture of the universe. A cluster contains many galaxies bound by their combined mass, along with hot gas and a deep envelope of dark matter that strengthens the gravitational connection between them. These environments reveal how matter organizes itself beyond the scale of individual galaxies, forming structures that stretch across millions of light years. The simplest of these associations are galaxy groups. Our own Milky Way belongs to a small group that includes the Andromeda Galaxy, the Triangulum Galaxy, and many smaller companions. Even at this scale, interactions influence how galaxies move and evolve. Over long periods, galaxies in a group may drift closer together, exchange material, or eventually merge. The motions are slow and guided by the collective gravitational pull of the entire system. Groups serve as the first step toward the formation of larger clusters, which contain far more galaxies and far more mass. Galaxy clusters are among the largest gravitationally bound structures in the cosmos. Within a cluster, galaxies move through a shared environment filled with extremely hot gas. This gas emits X-rays, allowing astronomers to detect and study it using specialized telescopes. The presence of this gas also confirms the strength of the gravitational field that holds the cluster together. Without sufficient mass, the gas would disperse into space. Instead, it remains anchored by the cluster's deep gravitational well, which is shaped both by visible matter and by the unseen influence of dark matter. Dark matter is an essential component of galaxy clusters. Its presence forms a large halo that surrounds and permeates the entire structure. Astronomers detect this halo by observing how galaxies move within the cluster and how the cluster bends light from objects lying behind it. This effect, known as gravitational lensing, provides clear evidence that clusters contain far more mass than what can be seen directly. The distribution of dark matter determines how tightly the cluster holds together and how galaxies move along their orbits within it. Clusters do not remain static. They grow over time as smaller groups and individual galaxies drift toward them and become part of their structure. The slow motion of these systems reflects the balance between gravity and the expansion of the universe. On small scales, gravity dominates, keeping galaxies bound. On larger scales, expansion stretches the distances between clusters. This balance creates a pattern in which clusters remain coherent, while the space between them increases gradually. When viewed on the scale of the cosmic web, clusters serve as nodes connected by long filaments of galaxies and gas. These connections reveal how matter flows across enormous distances, guiding the formation of even larger structures. The quiet movement of galaxies within clusters, combined with their role in the broader network, shows how the universe maintains its layered organization from one scale to the next. The pace at which clusters evolve is slow, unfolding across hundreds of millions or billions of years. This gradual motion creates a sense of calm when viewed in its full context. Nothing in these structures changes suddenly. Instead, they shift with a rhythm that matches the deep timescales of the cosmos. That same slow rhythm can be helpful as you rest. If your breathing is becoming more relaxed while you listen, that is a natural response to the steady pace of these cosmic processes. You may notice yourself sinking more comfortably into the quiet around you, just as these galaxies settle into their long, stable paths within the cluster. Further on, we will explore how dark matter shapes these vast environments, determining how clusters form and how they maintain their structure over immense periods of time. Galaxy clusters owe much of their stability to the presence of dark matter, a form of mass that does not emit or absorb light yet exerts a powerful gravitational influence. Although dark matter cannot be observed directly, its effects can be measured through the motion of galaxies, the behavior of hot gas, and the bending of light from distant objects. These measurements reveal that the majority of a cluster's mass is not contained in its stars or gas, but in a vast halo of dark matter that surrounds and permeates the entire structure. Without this unseen component, clusters would not be able to hold themselves together over billions of years. The gravitational field created by dark matter shapes every aspect of a cluster's structure. Each galaxy moves through the cluster along a path determined by the total distribution of mass, most of which lies in the dark halo. These orbits are not simple or circular. They shift gradually as clusters grow, merge, or change shape over long periods. Even so, the overall structure remains steady because the dark matter halo provides a consistent gravitational framework that keeps the system bound. The visible galaxies are like small, bright markers tracing out the larger shape defined by the invisible mass around them. Astronomers study dark matter in clusters through several complementary methods. One of the most important is gravitational lensing. When light from a distant galaxy passes near a massive cluster, the gravitational field bends its path, creating distortions in the image observed from Earth. The degree and pattern of this bending depend on the distribution of mass within the cluster. By measuring these distortions, scientists map the invisible halo, revealing how dark matter is arranged across vast distances. These maps show that dark matter forms smooth, extended structures that stretch far beyond the visible boundaries of the cluster. Another method involves studying the hot gas that fills the space between galaxies in a cluster. This gas reaches temperatures of millions of degrees and emits X-rays detectable by specialized telescopes. The temperature and distribution of the gas depend on the gravitational pull of the cluster. If there were not enough mass to confine the gas, it would escape into surrounding space. Instead, the gas remains bound, confirming the presence of a deep gravitational well. By analyzing the gas, astronomers can estimate the total mass of the cluster and compare it to the amount of visible matter. The difference reveals the contribution of dark matter. Dark matter also plays a role in how clusters evolve over time. As smaller groups or individual galaxies approach a cluster, they experience the gravitational attraction of the dark matter halo, which draws them inward. This process allows clusters to grow steadily, adding new members and increasing their overall mass. The same halo also stabilizes the cluster against internal disruptions. When galaxies pass close to one another or interact with the hot gas, these encounters can alter their motion, but the broader halo keeps the cluster as a coherent structure. The presence of dark matter in galaxy clusters also helps scientists understand the history and future of the universe. By studying how clusters form, how they grow, and how they are distributed across space, astronomers learn about the conditions present in the early universe. Clusters act as markers of the large-scale distribution of matter, showing how initial fluctuations evolved into the structures observed today. The relationship between dark matter and visible matter within clusters adds further detail to these observations. The structure of a galaxy cluster provides a clear example of how unseen components shape cosmic architecture. Even though dark matter cannot be observed directly, its gravitational influence determines the behavior of entire systems. Later, we will shift from clusters to the vast filaments that connect them, revealing how matter forms long, continuous structures that stretch across enormous distances. The vast structures of the universe become easier to understand when you examine the regions that lie between the long, extended strands where galaxies gather. These regions, known as voids, occupy a large portion of the cosmos. A void is not completely empty, yet it contains far less matter than the surrounding areas. The low density of these regions plays a vital role in shaping the universe, because matter naturally moves away from them as gravity draws material toward denser formations. This movement gradually increases the contrast between the sparse interiors of voids and the richer structures that surround them. Voids formed from the same early fluctuations that produced filaments and clusters. Areas that began with slightly lower density expanded more quickly than their surroundings. As space stretched over long periods, the differences became more pronounced. Matter drifted outward, leaving behind large areas with only a small number of galaxies. These galaxies tend to be isolated and often show characteristics that differ from those in more crowded environments. Their formation reflects the limited interactions available in such open regions, where gravitational encounters with neighboring systems occur much less frequently. Observations reveal that voids can span hundreds of millions of light-years. Despite this size, they do not exist as featureless gaps. Subtle patterns appear within them, formed by the small amount of matter present. The galaxies found inside them tend to be faint, often smaller than those in denser surroundings. Their distribution offers scientists clues about how matter behaves in extreme conditions, where gravitational influence is weaker and evolutionary pathways differ. Studying these systems provides insight into how environment affects the development of galaxies. Mapping voids requires large, detailed surveys that measure the positions of many galaxies across vast distances. These surveys reveal both the structures and the absences that define the cosmic landscape. By charting where galaxies do and do not appear, astronomers construct three-dimensional maps of the universe. These maps show that voids are not random gaps but integral parts of the overall architecture. The patterns formed by voids and filaments together create the familiar web-like arrangement observed at the largest scales. The boundaries of a void are shaped by the motion of matter along gravitational gradients. As material flows toward denser regions, the edges sharpen, forming clear transitions between the emptier interior and the surrounding structures. Over time, these boundaries may shift slightly as galaxies migrate outward or inward depending on the balance of forces acting upon them. Although the evolution is slow, it reveals how the universe adjusts itself through continuous, gentle movement influenced by the distribution of mass. Voids contribute to our understanding of cosmology in several important ways. Their size and distribution help scientists test models describing how the universe has expanded over long periods. Because voids amplify differences created by cosmic expansion, their properties provide clues about dark energy, which influences how quickly the universe grows. Voids also highlight the effects of dark matter by revealing how gravitational forces shape regions with little visible material. When models accurately predict the characteristics of voids, it strengthens confidence in the underlying physics. Even though voids contain fewer galaxies, they are no less important than the dense structures that often draw more attention. They offer a view into the quieter aspects of cosmic evolution, where matter develops under simpler conditions. This clarity helps researchers observe how gravity alone can sculpt the distribution of galaxies. By examining both dense and sparse environments, scientists gain a more complete picture of how the universe formed and continues to evolve. These expansive regions play a stabilizing role by allowing space for structures to develop and expand. Without voids, the cosmic web would not have its distinctive shape. They provide the contrast necessary for the universe to form its larger patterns, balancing the areas where matter gathers most strongly. As part of the overall structure, they illustrate how emptiness can contribute to order, revealing yet another way the cosmos arranges itself through the quiet, steady action of physical laws. When astronomers look across immense distances and gather light from countless galaxies, a clear pattern emerges. The universe is arranged in a broad, interconnected network where dense regions are linked by long strands and separated by wide, low-density expanses. This entire arrangement forms what is known as the cosmic web. It is the largest structural pattern observed in the universe, and it demonstrates how matter organizes itself under the combined influence of gravity, expansion, and the conditions present shortly after the earliest stage of cosmic history. The appearance of the cosmic web did not arise suddenly. Its structure reflects the gradual evolution of matter over billions of years. Differences in density present at early times grew slowly as gravity pulled material into certain regions while allowing other parts of space to expand more rapidly. As these variations amplified, clusters, filaments, and voids became more distinct. Observations show that these components fit together in a way that resembles a vast, irregular network stretching across space. The forms are not symmetrical or repetitive, yet they share consistent features that reveal the underlying physics. Mapping the cosmic web requires collecting measurements of galaxies positioned across large areas of the sky. Astronomers determine the distance to each galaxy by examining how its light is shifted toward longer wavelengths. This shift results from the expansion of space and allows scientists to estimate how far the light has traveled. By combining millions of such measurements, researchers construct three-dimensional maps that display where matter is concentrated and where it is sparse. These maps provide some of the most direct evidence of the cosmic web's structure. The patterns revealed by these surveys match the predictions made by computational models. When scientists simulate the evolution of matter under gravity, using initial conditions based on observations of the early universe, the resulting structures resemble the same web-like arrangements seen in real data. This agreement between simulation and observation strengthens confidence in the models used to describe cosmic evolution. It also confirms that the cosmic web is not an artifact of measurement, but a natural outcome of well-understood physical principles. The web itself consists of several components that work together to form the overall structure. Clusters occupy the densest regions where multiple strands intersect. Filaments extend outward from these nodes, carrying galaxies and gas along elongated paths. Voids fill the spaces between the filaments, creating expansive areas with very little matter. Each of these elements contributes to the stability of the network. Matter flows along the strands toward the denser centers, gradually reinforcing the pattern over time. Although the cosmic web appears static in images, it evolves slowly as the universe expands. Filaments may stretch or thin as distances increase, and clusters can continue to grow as they attract nearby matter. Yet the fundamental layout remains recognizable across long periods. This steadiness reflects the balance between gravitational attraction, which draws matter together, and cosmic expansion, which increases separation on the largest scales. The resulting form is one that maintains its shape even as its components shift in subtle ways. Studying the cosmic web helps astronomers understand the distribution of dark matter, which forms the framework upon which visible matter gathers. The gravitational influence of dark matter shapes the paths along which galaxies move and determines where structures become dense enough to form clusters. Because dark matter does not emit light, its presence must be inferred from the behavior of the galaxies and gas that trace the web. The close correspondence between visible structures and theoretical dark matter distributions provides strong evidence for its role in shaping the cosmos. The cosmic web also gives insight into how galaxies develop within different environments. Galaxies located in dense filaments or clusters often experience interactions that influence their evolution, while those in sparser regions may grow more slowly. These environmental differences help explain the wide variety of galaxy shapes, sizes, and behaviors observed across the universe. The web serves as both a map of matter distribution and a guide to understanding the forces that drive cosmic development. The vast scale of this structure highlights the coherence of the universe across distances too great to comprehend directly. It shows how simple physical laws can produce an intricate and balanced arrangement when given enough time. By observing the cosmic web, astronomers gain a clear view of the universe's architecture and the principles that guide its evolution. It stands as one of the most striking examples of how the cosmos forms order through gradual change governed by consistent natural laws. The existence of large-scale patterns across the universe raises an important question. Why did matter arrange itself this way in the first place? The structures observed today can be traced back to conditions present long before galaxies, stars, or planets formed. During that early stage, the universe was filled with hot, dense plasma that expanded and cooled over time. Although this environment was nearly uniform, it contained slight variations in density. These small differences played a defining role in shaping everything that would follow. The early universe behaved like a fluid responding to pressure and gravity, Regions with slightly higher density exerted a stronger gravitational pull, while areas with lower density expanded more rapidly. As the universe grew, these variations became more pronounced. Where matter accumulated, the pull of gravity increased, encouraging even more material to gather. This feedback process gradually amplified the initial irregularities. Over extremely long periods, these variations provided the seeds for all later structures. Observations support this view through measurements of faint radiation left from the earliest stage of cosmic evolution. This radiation carries subtle patterns that match the expected distribution of early density fluctuations. The slight differences recorded in these measurements correspond directly to the large-scale structures visible today. What appear as immense clusters, filaments and voids began as tiny imbalances that grew steadily as the universe expanded. These observations form one of the most reliable foundations for understanding cosmic structure. As matter flowed toward regions of higher density, it formed the first stable groupings under the influence of gravity. These early concentrations developed into the building blocks of larger structures. Over time, they merged, shifted, and increased in complexity, eventually giving rise to the galaxies and clusters that populate the cosmos. Despite the vast differences in scale between early fluctuations and modern structures, both arise from the same basic principles: small initial variations shaped by gravity over long periods. The growth of early density fluctuations depended not only on gravity but also on the balance of forces acting in the young universe. Pressure created by the energetic particles present at that time resisted collapse. This interplay between pressure and gravity produced patterns that can still be traced today. Once the universe cooled enough for atoms to form, matter became more responsive to gravitational influence, allowing fluctuations to grow more quickly. This transition marked a major turning point in the development of cosmic structure. The distribution of early matter was not perfectly smooth or entirely random. Certain wavelengths of fluctuation grew more efficiently than others, due to the physical conditions present. These patterns influenced the spacing of the large-scale structures that formed later. As matter assembled into increasingly complex arrangements, these underlying patterns remained imprinted in the organization of galaxies. Modern observations confirm these relationships, demonstrating the continuity between early conditions and present-day structure. Dark matter played a central role even at this early stage. Although it does not interact with light, it provided most of the gravitational influence that shaped the formation of large-scale structures. Dark matter began to gather into extended regions, where gravitational forces collected ordinary matter. These concentrations formed the backbone of what would become the cosmic web. By tracing the distribution of galaxies today, scientists gain insight into where dark matter was most concentrated in the early universe. Understanding how small fluctuations grew into the structures observed now requires precise measurements and complex calculations. Yet the underlying concept remains simple. Slight differences in density allowed gravity to take hold and guide the development of the cosmos. Each change took place slowly, following consistent physical laws. The universe's large-scale structure is the natural outcome of these processes, shaped by forces that have remained steady across its entire history. The remarkable aspect of this evolution is how early conditions influenced events billions of years later. The small variations imprinted in the young universe had long-lasting effects, guiding the formation of every cluster and filament visible today. By studying these early conditions, astronomers gain a deeper understanding of how the cosmos reached its present form and how it may continue to develop as time progresses. The large patterns that fill the universe today emerged through changes that unfolded over astonishing stretches of time. These timescales are so vast that ordinary measurements lose their meaning when compared with the processes shaping galaxies, clusters, and the broader cosmic web. Each stage of development progresses at a pace that is almost imperceptible when viewed from a human perspective. Yet over billions of years, these gradual shifts accumulate into the structure observed across the sky. The expansion of the universe plays a central role in this slow transformation. As space grows, distances between large structures increase, creating room for patterns to stretch and settle into new positions. Despite this expansion, gravity continues to draw matter together, in regions where density is higher. The interaction between these two influences produces a gentle tension that guides the development of structure. Regions of higher density grow more pronounced as matter continues to collect, while areas of lower density expand more quickly and become more isolated. Galaxies within these regions follow stable paths determined by the forces acting upon them. Their internal evolution also contributes to the broader picture. Stars form, age, and eventually release material back into surrounding space. These processes occur repeatedly, gradually enriching the environments where new stars take shape. Although a single star's life may seem long, it is only a brief moment within the timescales governing cosmic evolution. The combined actions of countless stars influence the overall appearance and behavior of galaxies as they adapt to changing conditions. Clusters evolve even more slowly than individual galaxies. Their immense mass gives them a stability that resists sudden change. Galaxies within a cluster move through the shared gravitational field, tracing paths that shift gently over long periods. Interactions between these galaxies occur, but on timescales far longer than those governing the evolution of a single star or planetary system. The cluster's overall structure remains recognizable across enormous spans of time, even as its components experience subtle changes. The slow pace of cosmic evolution allows structure to develop consistently, without disruption. Gravity operates steadily, guiding matter along paths that remain predictable across billions of years. The expansion of space influences these movements but does not erase the patterns that gravity establishes. Instead, expansion stretches the existing structure, expanding the distances between clusters while leaving the internal arrangement of galaxies within those clusters largely unchanged. This balance produces a universe that evolves gradually rather than abruptly. Observing this slow evolution requires tools capable of detecting changes across great distances and long periods. Light from distant galaxies carries information about their earlier states, allowing astronomers to reconstruct aspects of cosmic history. By comparing distant regions with nearby ones, scientists trace the progression of structure from early times to the present. These comparisons reveal trends that confirm theoretical models describing how matter responds to gravity and expansion. The quiet nature of these changes gives the universe a sense of steadiness. Nothing forms or dissolves rapidly on the scale of the cosmic web. Instead, matter drifts, gathers, and reshapes itself with a calm persistence. The rhythm of this evolution mirrors the consistent influence of physical laws that have guided the cosmos since its earliest moments. Each stage builds upon the last, creating a seamless continuity between past and present. As these patterns unfold, the scale of time involved can encourage a similar sense of ease in anyone reflecting on them. Cosmic evolution is unhurried, shaped by processes that move forward without haste. If your breathing has begun to settle into a slower cadence while listening, that is a natural response to the steady pace of these ideas. The universe itself unfolds with a quiet patience, and noticing that rhythm may help you settle more deeply into rest. The understanding of how these long timescales influence structure deepens appreciation for the cosmos as a whole. It reveals that the universe is not a static picture but a dynamic environment shaped by continuous, gentle motion. By recognizing the slow pace at which these changes occur, it becomes easier to see how the structures observed today connect to processes that began long before the first galaxies formed. The role of dark matter becomes clearer when you look at how matter gathered into the earliest structures of the universe. Ordinary matter alone could not have formed the patterns observed today. Its interactions with radiation in the early environment prevented it from collapsing efficiently. Dark matter, however, responded only to gravity and began forming extended regions of higher density long before ordinary matter could follow. These regions acted as gravitational anchors, drawing in gas that eventually formed the first stars and galaxies. Without dark matter, the universe would look very different, lacking the pronounced structures that give shape to the cosmic web. Dark matter does not emit light, absorb it, or scatter it. Its presence can only be inferred from the gravitational influence it exerts. Observations of galaxy motions reveal that visible matter accounts for only a small fraction of the mass required to keep galaxies bound. Stars move too quickly to remain in stable orbits unless an unseen mass provides the necessary gravitational pull. This additional mass surrounds galaxies in wide halos extending far beyond the regions filled with visible stars. These halos dictate how galaxies rotate, how they interact, and how they evolve over long periods. The influence of dark matter becomes even more pronounced on larger scales. In the early universe, dark matter began to gather into elongated regions where gravitational forces encouraged material to accumulate. These early concentrations formed the scaffolding upon which the cosmic web would later develop. Ordinary matter gradually settled into these dark matter structures as the universe cooled and expansion reduced the influence of radiation. Over billions of years, gas collected along the same paths traced by dark matter, producing the filaments and clusters observed in modern surveys. Simulations confirm the central role of dark matter in shaping large-scale structure. When models include dark matter with properties inferred from observations, the resulting patterns match the universe closely. The positions of clusters, the thickness of filaments, and the size of voids all arise naturally from dark matter distributions. If dark matter is removed from the simulation, the universe fails to develop coherent structures. Galaxies do not cluster, filaments do not form, and large voids do not appear. This strong dependence on dark matter highlights its importance in guiding the formation of structure. The gravitational influence of dark matter is subtle on small scales but becomes dominant over larger distances. Within galaxies, dark matter shapes rotation patterns and stabilizes the systems against disruption. Between galaxies, it forms extended halos that overlap and interact, influencing how galaxies move relative to one another. Across clusters and filaments, dark matter determines the overall landscape of the cosmic web. It defines where matter collects, how flows develop, and how structure grows as time passes. Understanding dark matter also helps explain how galaxies differ depending on their environment. Regions with greater concentrations of dark matter tend to form galaxies earlier and more efficiently. These galaxies may evolve rapidly due to the strong gravitational forces present. In contrast, regions with lower dark matter density form fewer structures, leading to sparse or irregular galaxy populations. By studying these variations, astronomers gain insight into how dark matter shapes the life cycle of galaxies from their earliest stages to their current states. Although dark matter remains mysterious, its gravitational effects are reliable and predictable. It interacts through gravity in a way that allows scientists to calculate its influence on both small and large scales. The agreement between theory and observation strengthens the understanding that dark matter is essential for cosmic structure. Research continues to investigate its exact nature, but its role in shaping the universe is firmly established. The stability and form of the cosmic web reflect how dark matter has guided the movements of ordinary matter across immense periods of time. Through its quiet influence, it created the conditions necessary for galaxies to assemble into clusters, align along filaments, and define the boundaries of vast voids. Even though it cannot be seen directly, dark matter shapes nearly every aspect of the universe's large-scale architecture, revealing itself through the orderly patterns it helps create. Dark energy introduces another dimension to the way cosmic structure evolves, even though it does not interact with matter in the same way gravity does. Its presence is inferred from observations showing that the expansion of the universe is not slowing down, as once expected, but accelerating. This acceleration affects the largest scales of the cosmos, gradually altering the spacing between structures while leaving smaller regions bound by gravity relatively unchanged. Understanding how dark energy influences cosmic development helps explain why the universe appears the way it does today. The discovery of accelerated expansion came from precise measurements of distant stellar explosions that serve as consistent brightness markers. By comparing their brightness with their redshift, astronomers determined that these explosions were farther away than predicted by models of a steadily expanding universe. This unexpected result indicated that expansion had begun increasing in speed. The simplest explanation was the presence of an energy component permeating space, producing a gentle but persistent outward pressure. This pressure affects the cosmos uniformly, shaping the behavior of galaxies and clusters across vast distances. Dark energy does not function like the gravitational forces that hold galaxies together or draw matter into filaments. Instead, it influences the fabric of space itself, encouraging expansion even in regions where matter is sparse. Over long timescales, this influence changes the arrangement of large structures by increasing the distances between them. Clusters remain gravitationally bound, maintaining their internal stability, but the space separating them gradually stretches. This process alters how structures relate to one another while preserving their internal coherence. The effects of dark energy become more noticeable as distances grow. On the scale of individual galaxies or clusters, gravity dominates, sustaining the integrity of these systems. However, when comparing regions separated by hundreds of millions of light-years, expansion becomes a significant factor. Filaments may appear to lengthen or thin as the space between their components stretches. Voids grow larger, not because matter is moving out of them quickly, but because space itself expands within their boundaries. These changes happen gradually, following a smooth progression rather than sudden transitions. Models that incorporate dark energy align closely with observed patterns across the universe. They predict how structures should appear at different eras of cosmic history and how those structures change as expansion accelerates. By comparing these predictions with large surveys, astronomers confirm that dark energy plays a consistent role in shaping the cosmos. Without it, the universe would show a different distribution of matter, with structures positioned more closely and expansion slowing rather than speeding up. The presence of dark energy helps explain why distant galaxies appear fainter and more widely spaced than they would under models without acceleration. The influence of dark energy also affects the future development of cosmic structure. As expansion continues, galaxies within clusters will remain bound to one another, but their interactions with neighboring clusters will diminish. The distances separating large structures will become too vast for gravitational attraction to overcome expansion. Over extremely long periods, the cosmic web may appear more stretched, with clusters becoming increasingly isolated. Filaments may lose some of their definition as the space between galaxies widens. Even with these changes, local gravitational systems such as galaxies and clusters continue to evolve independently, maintaining their internal balance. Although dark energy remains one of the least understood components of the universe, its effects are clear and measurable. It shapes the large-scale structure by controlling how distances grow across cosmic time. Its influence is subtle yet decisive, guiding the long-term evolution of the universe in a direction that emphasizes expansion rather than contraction. By observing the patterns formed by galaxies, clusters, and voids, astronomers gain insight into how dark energy interacts with the cosmos as a whole. This energy component highlights the complexity of the universe's behavior on the largest scales. The combination of gravitational attraction, cosmic expansion, and accelerated growth creates a dynamic landscape that evolves slowly yet consistently. Dark energy provides the context in which all structures develop, determining how they relate to one another as time progresses. Its steady influence continues to shape the future arrangement of matter across space, revealing another layer of the physics guiding the universe from its earliest moments to its distant future. Ordinary matter, also called baryonic matter, forms the familiar components of the universe: stars, planets, gas, and dust. Although it represents only a small fraction of the total mass present, its behavior shapes much of what is visible. Understanding how this type of matter moves through the cosmic web provides insight into how galaxies form, how stars emerge, and how large-scale structures maintain their coherence over time. Baryonic matter responds not only to gravity but also to heating, cooling, pressure, and interactions with radiation, giving it a rich and varied influence on cosmic evolution. Much of the baryonic matter in the universe exists in the form of gas spread throughout intergalactic and interstellar space. In the vast volumes between galaxies, this gas is often warm or hot, depending on the processes acting upon it. As gas moves through filaments, it follows the gravitational landscape created by dark matter. The gas flows gently toward regions where the gravitational pull is strongest, settling into the elongated paths of the cosmic web. As it accumulates, its density increases, creating the conditions required for star formation within galaxies. The distribution of gas within filaments and clusters plays a major role in determining how galaxies grow. Gas that cools efficiently can sink deeper into gravitational wells, providing fresh material for the formation of new stars. Gas that remains hot due to the energetic environments within clusters resists collapse and slows the formation of additional stars. These differences in temperature and density explain why galaxies in different environments often follow distinct evolutionary paths. In quieter regions, gas may cool steadily, allowing star formation to continue for long periods. In dense clusters, heating from surrounding activity can limit or even halt the growth of new stars. Interactions between gas and radiation also shape the movement of baryonic matter. When energetic events such as stellar explosions or active galactic cores release radiation, they heat nearby gas and push it outward. This movement redistributes matter across space, altering the supply of gas available to form new stars. In some regions, these processes enrich the gas with heavier elements created inside stars. When this enriched material mixes with cooler gas, it helps shape the chemical composition of future generations of stars and planetary systems. Dust particles, although much smaller in quantity than gas, play a significant role as well. These tiny grains absorb and scatter light, influencing how energy moves through galaxies. Dust helps regulate the temperature of gas clouds, shaping the environment in which stars form. Over time, dust grains also participate in the creation of planets, as they collide and stick together in the disk surrounding young stars. Their presence adds another layer of complexity to the behavior of baryonic matter. The movement of baryonic matter within galaxies reveals how internal and external forces work together. Spiral galaxies display organized patterns in their rotating disks, where waves of higher density encourage gas to compress and form stars. Elliptical galaxies show a more uniform distribution, shaped by past interactions and mergers that have redistributed gas and stars in a smoother arrangement. Regardless of the type of galaxy, baryonic matter adjusts itself according to the gravitational environment while also responding to internal processes such as stellar evolution and feedback from energetic events. Beyond individual galaxies, baryonic matter contributes to the appearance and behavior of clusters. Hot gas, held within the gravitational wells of clusters, emits radiation observable in X-rays. This gas helps reveal the total mass of a cluster and its internal structure. Over time, the gas moves slowly within the cluster's gravitational field, interacting with galaxies and influencing how they evolve. Even though dark matter dominates the cluster's overall mass, baryonic matter provides important information about the cluster's history and the processes shaping it. By examining how baryonic matter flows through the cosmic web, astronomers better understand the link between large-scale structure and the development of individual galaxies. The movement of gas, the formation of stars, and the redistribution of material over long periods all contribute to the evolving appearance of the universe. Baryonic matter serves as the visible expression of the deeper gravitational framework shaped by dark matter, making it essential for interpreting the patterns observed across the cosmos. The behavior of gas between galaxies provides important insight into how matter circulates through the cosmic web. This intergalactic medium exists in various states, ranging from warm, diffuse clouds to extremely hot plasma found in dense environments. Although it is not as visible as the stars within galaxies, the intergalactic medium contains a significant portion of the universe's baryonic matter. Its movement, heating, and cooling shape the conditions under which galaxies grow and evolve over long stretches of time. In regions between clusters and filaments, the gas is often warm and thinly distributed. It traces the paths carved out by dark matter, following gravitational gradients that guide its motion. As gas flows along these paths, it becomes gradually compressed in the denser regions of filaments. This compression increases temperature and pressure, altering the physical state of the gas and sometimes triggering shocks that heat it further. These processes reveal how matter responds to variations in density and gravitational influence across large distances. Within clusters, the gas reaches much higher temperatures due to the motions of galaxies and the strong gravitational pull. As galaxies move rapidly through the cluster environment, they stir the surrounding gas, creating turbulence and mixing material from different regions. The combined effect of these motions heats the gas to millions of degrees, causing it to emit radiation detectable in the X-ray portion of the spectrum. Observations of this emission allow astronomers to measure the temperature and density of the gas, providing clues about the total mass contained within the cluster. Gas can escape from galaxies and enter this broader environment through several mechanisms. Stellar explosions release powerful winds that push gas outward. Active galactic cores can expel material across great distances, adding energy to the intergalactic medium. These outflows distribute elements created inside stars into the space between galaxies. Over long periods, this enriched material cycles back into galaxies or remains suspended in intergalactic space, contributing to the overall composition of the cosmic web. Cooling processes also play a significant role in shaping the intergalactic medium. As hot gas radiates energy, it gradually cools and becomes more capable of flowing into galaxies. This cooling provides fresh material for star formation and sustains the ongoing development of galaxies. However, the balance between heating and cooling varies depending on environment. In clusters, heating processes often dominate, preventing gas from cooling enough to collapse into new stars. In less crowded regions, cooling proceeds more efficiently, supporting steady star formation over time. Interactions between galaxies and the intergalactic medium influence both components. When galaxies move through dense gas, they can lose material from their outer regions. This process, known as stripping, alters the galaxies by reducing their supply of gas available for star formation. At the same time, the stripped material becomes part of the intergalactic medium, enriching it with elements and changing its composition. These exchanges demonstrate how the intergalactic environment and galaxies remain interconnected, shaping one another across long periods. The intergalactic medium also helps explain how structures such as filaments maintain their form. Gas flowing into these elongated regions provides a steady supply of material that reinforces the gravitational patterns established by dark matter. This flow continues as long as gravitational forces guide matter toward denser areas. Over time, the accumulation of gas contributes to the growth of galaxies within the filaments, linking the largest structures of the cosmic web to the development of individual systems. Studying the intergalactic medium requires advanced instruments capable of detecting faint signals from distant regions. Observations using ultraviolet and X-ray wavelengths allow scientists to identify the physical conditions of the gas and measure its distribution. These measurements, combined with surveys of galaxies, provide a comprehensive picture of how matter moves through the universe. Together, they reveal a dynamic environment shaped by gravity, heating, cooling, and the continual exchange of material between galaxies and the space around them. The interplay between these processes highlights the complexity of the cosmic web. The intergalactic medium is not static but constantly influenced by the motion of galaxies, the impact of energetic events, and the effects of large-scale gravitational forces. Its behavior contributes to the overall structure of the universe, revealing how matter binds together across immense distances and evolves over time. By examining this diffuse, often invisible component, astronomers gain a deeper understanding of the cosmic environment that shapes the development of galaxies and large-scale patterns. Galaxies grow and evolve through a continuous cycle of change, influenced by both internal processes and the environments through which they move. Their structure reflects the combined effects of gravity, gas dynamics, stellar evolution, and interactions with neighboring systems. By examining how galaxies transform over long periods, astronomers gain insight into the mechanisms that shape the visible universe. These transformations occur slowly yet persistently, following physical laws that remain consistent across cosmic time. Stars form within clouds of gas that collapse under their own weight. As the gas becomes denser, it cools and fragments into smaller regions where individual stars take shape. The energy released during star formation can heat surrounding gas, regulating the pace at which new stars appear. Throughout a galaxy's life, This balance between cooling and heating determines how actively new stars are created. Over time, regions that have produced many stars may become depleted of gas, while other areas continue to supply material for future generations of stars. The evolution of stars influences the broader galaxy as well. When a star completes its life cycle, it often expels material into surrounding space. This material includes heavier elements formed inside the star, enriching the gas available for future star formation. Over long periods, these cycles shape a galaxy's chemical composition. Galaxies with long histories of active star formation contain higher proportions of such elements, while younger or less active galaxies remain richer in lighter elements. This gradual enrichment process affects the types of stars and planetary systems that form later. Interactions between stars also shape galactic structure. In dense environments, gravitational encounters can alter the paths of stars, leading to gradual changes in a galaxy's shape. Spiral galaxies, for example, maintain their graceful patterns through the combined motions of stars and gas, guided by density waves that move through their disks. These waves encourage gas clouds to compress, creating new sites for star formation. Over time, this process reinforces the familiar spiral structure, while allowing slow adjustments to occur as stars drift through the galaxy. Galaxies do not evolve in isolation. They move through the cosmic web, encountering other systems along the way. When two galaxies pass near each other, their gravitational fields interact, distorting their shapes and altering their internal motions. Close encounters can trigger bursts of star formation by compressing gas or disrupting existing patterns. If galaxies merge, the process can significantly reshape their structure. The resulting system may take on a new form, often becoming more spherical or irregular as stars settle into new orbits. These interactions are more common in dense environments where many galaxies reside close together. In such regions, galaxies experience repeated encounters that gradually influence their appearance and behavior. Over billions of years, these interactions contribute to the variety of galaxy types observed across the universe. Some galaxies become smooth and elliptical through repeated mergers, while others maintain their disk-like structures by avoiding major collisions. The environment in which a galaxy resides plays a significant role in determining its long-term evolution. Gas flows also contribute to galactic change. Galaxies can draw in gas from surrounding space, replenishing their supply for star formation. They can also lose gas through energetic events such as stellar explosions or the activity of central black holes. These processes regulate the availability of material needed to create new stars, influencing how quickly a galaxy grows or how its appearance changes. Over time, the balance of inflows and outflows shapes a galaxy's overall development. The presence of a central black hole adds another layer of complexity. Many galaxies contain a massive object at their core that can release tremendous amounts of energy when gas falls toward it. This energy can heat or expel gas, altering the conditions required for star formation. In some galaxies, such activity slows the creation of new stars by removing or heating the gas needed to form them. In others, the effects may be more subtle, influencing only the central regions. The relationship between black holes and galaxies evolves over long periods, with each affecting the growth and structure of the other. The gradual evolution of galaxies reflects the interplay between many forces acting across time. Their changing shapes, star formation histories, and chemical compositions reveal how matter responds to internal dynamics and external influences. By observing galaxies at different stages of development, astronomers piece together the long narrative of cosmic structure. Each galaxy carries the imprint of processes that have shaped it over millions or billions of years, forming part of the larger pattern that fills the universe. The environments surrounding galaxies play a crucial role in shaping how they grow and evolve. These environments range from isolated regions where galaxies drift with few interactions to dense clusters where encounters are frequent and gravitational forces are strong. Each type of environment imposes different conditions that influence the movement of gas, the formation of stars, and the long-term structure of galaxies. Understanding these surroundings provides insight into how the universe develops patterns on both small and large scales. In relatively quiet regions, galaxies experience minimal external disturbance. Here, Their evolution is guided primarily by internal processes such as the balance between gas cooling and heating, the formation of stars, and the gentle redistribution of material through stellar winds. These galaxies often maintain orderly structures for extended periods. Their spiral arms may remain well-defined, their disks stable, and their gas supplies available for steady star formation. Over time, these tranquil environments allow gradual, predictable development shaped mainly by internal physics rather than external forces. In contrast, dense regions present an entirely different set of conditions. Clusters contain large numbers of galaxies moving within a shared gravitational field. Their motions can be rapid, leading to encounters that alter their structure or remove gas from their outer regions. When a galaxy moves through the hot, dense gas filling a cluster, that gas can exert pressure strong enough to strip material from the galaxy's disk. This process reduces the supply of gas available for forming new stars, gradually changing the galaxy's appearance and limiting its ability to grow. Interactions between galaxies in clusters further influence their evolution. Close approaches can distort galactic shapes, triggering waves of star formation as gas compresses under tidal forces. Repeated interactions can transform galaxies over long periods, smoothing their structures or altering the distribution of stars. Many galaxies found in clusters show signs of such interactions, with shapes that reflect past encounters. These changes illustrate how environmental conditions guide the development of galaxies through a combination of gravitational forces and material exchange. Filaments provide another type of environment, bridging the space between clusters and connecting different regions of the cosmic web. Galaxies within filaments experience a mix of influences. They remain far enough apart to avoid constant interactions but close enough to feel the gravitational pull guiding material along the filament's length. Gas flowing through these structures can supply galaxies with the material needed to form new stars. This steady inflow helps maintain star-forming activity, allowing galaxies to grow even as they move through the extended landscape defined by dark matter. Voids, with their low density and wide separation between galaxies, offer yet another environment. Galaxies found in these regions tend to evolve slowly due to the limited availability of gas and the absence of strong external forces. Without frequent interactions or abundant material, their growth is gradual. These galaxies provide an important contrast to those in clusters, showing how sparse environments encourage different patterns of development. Their isolation allows astronomers to study how internal processes shape galaxies when external influences are minimal. Across all environments, the influence of dark matter provides a consistent gravitational framework. It defines the shape of clusters, filaments, and voids, guiding the movement of galaxies and determining the pathways along which gas flows. This framework ensures that even though environments differ widely, the underlying patterns follow the same basic physical principles. Galaxies respond to these patterns in ways that reflect their local surroundings while remaining part of the broader cosmic structure. The quiet, steady nature of these environments mirrors the overall rhythm of the universe. Each region evolves according to familiar physical laws, changing gradually as matter moves through space. If you notice your breathing settling into a slower, more comfortable pace while listening, that reflects the calm progression of these cosmic processes. The universe grows and transforms without haste, offering a sense of ease that can naturally support rest. Understanding how environments influence galaxies helps reveal why the universe contains such a wide range of forms. From spiral galaxies with graceful arms to smooth elliptical systems shaped by past interactions, each reflects the conditions of its surroundings. By examining these environments, astronomers piece together the story of how matter has organized itself across billions of years, creating a cosmos filled with diversity yet governed by consistent physical principles. Galaxies are not the only structures influenced by their environments. On even larger scales, the gravitational forces at work shape the movement of entire groups of galaxies as they drift through the cosmic web. These groups, typically containing a few dozen galaxies, occupy the middle ground between isolated systems and massive clusters. Their evolution reveals how matter transitions from small-scale organization to the broader patterns that define the universe's architecture. A group forms when several galaxies become gravitationally bound, sharing a common center of mass. The motions of these galaxies reflect their shared gravitational relationship rather than the influence of more distant structures. Over long periods, galaxies within a group move along paths determined by the distribution of mass in their surroundings. Their orbits can appear irregular when viewed over short timescales, but when observed across millions of years, they follow predictable trajectories shaped by the group's overall gravitational potential. Groups provide environments where interactions are more common than in isolated regions, but less intense than in dense clusters. Because the galaxies are relatively close, their gravitational fields can influence one another, leading to gradual changes in structure or the redistribution of gas. These interactions may trigger episodes of star formation or alter the shapes of galaxies. However, the encounters are generally gentler than those found in clusters, allowing systems to retain their basic structure for longer periods. The distribution of dark matter within a group defines the framework in which these interactions occur. A group's dark matter halo extends far beyond the visible boundaries of the galaxies it contains. This halo binds the group together, providing the gravitational pull that maintains coherence. The shape of the halo influences how galaxies move within the group and determines the stability of the entire system. Accurate measurements of galaxy motions help astronomers estimate the amount and distribution of dark matter in these regions, revealing how it supports the group's structure. Gas also plays an important role in group environments. Although the intergalactic medium in groups is less dense than in clusters, it still affects the movement of galaxies and the availability of material for star formation. When gas accumulates in a group, it can cool and flow toward individual galaxies, replenishing their supplies. In some groups, energetic events such as stellar explosions or activity from central black holes distribute gas more evenly across the environment. These processes influence how galaxies evolve by shaping the availability of material needed to form new stars. Groups serve as the building blocks of larger cosmic structures. Over long periods, they may fall into clusters or merge with neighboring groups. These mergers contribute to the growth of clusters and help shape the distribution of galaxies within them. The gradual movement of groups through the cosmic web shows how matter is not fixed in place but continually drifting under the influence of gravity. The interactions between groups and their surroundings reveal the dynamic nature of the cosmic landscape. The study of groups provides insight into the transitional stages of cosmic evolution. They show how galaxies assemble into larger units and how these units eventually become part of vast structures. Observing groups at different distances allows astronomers to trace their development over time, revealing how the universe gradually organizes itself into the patterns visible today. These observations help connect the evolution of individual galaxies with the large-scale processes that shape the cosmic web. Groups also demonstrate the varied environments in which galaxies develop. Some groups remain stable for long periods, experiencing only gentle interactions that preserve the structure of their members. Others undergo significant change as they drift toward clusters or encounter energetic events that reshape them. These differences show how the behavior of galaxies depends not only on their internal properties but also on the gravitational and material conditions of their surroundings. By examining galaxy groups, astronomers learn how structure develops across different scales. From individual galaxies to vast clusters, each level reveals patterns shaped by gravity, gas dynamics, and cosmic expansion. Groups illustrate how these forces work together to guide the long-term evolution of matter. Their movements, interactions, and gradual transformations provide a bridge between the smaller details of galactic evolution and the large-scale structure that fills the universe. The movement of galaxies through the cosmos reflects a balance between gravitational attraction and the expansion of space. Although expansion increases the distances between structures on the largest scales, gravity remains strong enough within certain regions to keep groups and clusters together. The interplay between these forces shapes the paths of galaxies, creating patterns that extend across hundreds of millions of light years. By observing these motions, astronomers gain insight into the distribution of mass and the underlying physics that govern the universe. Each galaxy moves through space with a combination of internal motion and the broader flow dictated by cosmic expansion. The motion relative to surrounding galaxies is influenced by gravitational forces acting across large distances. When a region contains more mass than its surroundings, it pulls neighboring galaxies toward it, creating coherent patterns of motion. These flows reveal where matter is concentrated and how gravitational forces shape cosmic structure. Over time, galaxies drift along these pathways, gradually defining the large-scale arrangement observed in surveys. The influence of cosmic expansion becomes more apparent when examining galaxies separated by great distances. The space between them stretches as the universe grows, increasing the separation even if they are not moving relative to one another through local gravitational interactions. The expansion does not act like a force pushing galaxies apart. Instead, it results from the changing geometry of space itself. This change produces the observed redshift in the light of distant galaxies, allowing astronomers to measure how quickly space is expanding and how that expansion has changed over time. Despite this expansion, galaxies within gravitationally bound structures remain connected. Clusters, for example, do not grow apart internally. The gravitational strength of the cluster outweighs the influence of cosmic expansion, keeping its galaxies in stable orbits around the cluster's center of mass. Groups of galaxies behave similarly, maintaining their coherence even as the space between large structures increases. These local systems illustrate how gravity can counteract the effects of expansion on smaller scales, preserving structure within an expanding universe. When considering the largest patterns in cosmic motion, astronomers observe broad flows of matter toward regions of higher density. These flows help explain how structures such as clusters and superclusters grow over long periods. As galaxies move through the cosmic web, they follow the gravitational contours shaped by dark matter. The movement is gentle yet persistent, gradually guiding matter toward the densest parts of the network. Over billions of years, this slow drift reinforces the structure of the cosmic web and contributes to the formation of increasingly complex arrangements. The study of cosmic flows also reveals how matter is distributed in regions that cannot be observed directly. By measuring how galaxies move relative to one another, astronomers infer the gravitational pull of unseen mass. These measurements provide evidence for dark matter and help map its distribution across the universe. When flows converge on regions where no visible structures exist, it suggests the presence of large amounts of dark matter shaping the movement of galaxies. Such observations deepen the understanding of the universe's underlying framework. Changes in cosmic motion occur gradually. The paths of galaxies shift slowly as gravitational forces evolve and as expansion continues. Over immense periods, these small adjustments accumulate, altering the arrangement of matter. The slow pace of these changes mirrors the broader rhythm of the cosmos, where structure grows not through sudden events but through steady, long-term processes. This steady progression reflects the balance of forces guiding the universe as it evolves from its early stages to its current state. The patterns revealed by cosmic motion demonstrate the coherence of the universe on large scales. Galaxies do not move randomly but follow paths shaped by the distribution of mass and the expansion of space. These paths provide a record of how structure formed and how it continues to develop. By studying these motions, astronomers learn how galaxies respond to the forces acting upon them and how the universe maintains its overall structure across billions of years. Examining the movement of galaxies helps create a clearer picture of the cosmos as a dynamic environment. Each galaxy participates in the larger flow of matter, guided by gravity and influenced by expansion. The resulting patterns reveal how the universe arranges itself into the structures observed today, connecting the motions of individual systems to the vast network spanning space. Through these observations, the long-term evolution of the cosmos becomes easier to understand, highlighting the delicate balance of forces shaping its development. The large-scale structures of the universe do not arise solely from the behavior of matter. They also reflect the underlying geometry of space, which shapes how gravity operates and how matter responds to the expansion of the cosmos. Geometry in this context refers not to recognizable shapes but to the fundamental properties of space itself. These properties determine how distances behave, how light travels, and how matter influences the curvature of space. Understanding these aspects helps explain why the universe contains the patterns observed across such enormous scales. Einstein's theory of general relativity provides the foundation for understanding cosmic geometry. According to this theory, mass and energy cause space to curve. This curvature affects the motion of objects and the path of light. When a region contains a large amount of mass, the curvature becomes stronger, guiding the movement of galaxies and bending the light that passes nearby. The cosmic web forms within this curved landscape, with structures developing along pathways defined by the underlying geometry. On the largest scales, the universe appears to have a nearly uniform geometry, with slight variations determined by the distribution of matter. This uniformity allows astronomers to use the relation between distance and redshift to understand cosmic expansion. As the universe grows, the geometry of space stretches, altering how far light must travel from distant objects. By measuring these changes, astronomers build models that describe the universe's shape and how it has evolved over time. Even small variations in geometry can have significant effects. When light travels through regions with large concentrations of matter, the curvature of space alters its path. This bending, known as gravitational lensing, provides valuable information about the mass distribution in the universe, including the presence of dark matter. In some cases, lensing produces distorted or magnified images of distant galaxies, revealing how the geometry of space interacts with the structures within it. These distortions act as natural probes, allowing astronomers to map the invisible framework of mass shaping the cosmic web. Curvature also influences the growth of cosmic structure. In regions where mass density is higher, curvature becomes more pronounced, enhancing gravitational attraction. This increased attraction helps concentrate matter into clusters and filaments. In regions with lower density, curvature is weaker, allowing space to expand more freely and contributing to the formation of voids. The balance between curvature and expansion creates a dynamic environment in which structure develops gradually. One of the most striking aspects of cosmic geometry is how smoothly it connects the smallest and largest scales. The same principles that guide the motion of stars around a galaxy also govern the behavior of galaxies within clusters. The difference lies only in scale, not in the underlying physics. This consistency allows astronomers to apply observations across a wide range of environments, building models that describe the universe with remarkable accuracy. Recent observations suggest that the overall geometry of the universe is close to flat, meaning that parallel lines would remain parallel even across immense distances. This flatness has important implications for cosmic evolution. It indicates that the density of matter and energy is nearly balanced in a way that allows expansion to continue without collapsing or accelerating uncontrollably. Dark energy plays a key role in maintaining this balance, shaping the large-scale behavior of space while allowing structure to form naturally within it. Despite this apparent flatness, local variations in geometry remain significant. The curvature around clusters and filaments influences how galaxies move and how light behaves. These variations create the intricate patterns observed in large-scale surveys, highlighting the connection between matter and geometry. By measuring these patterns, astronomers refine their understanding of the universe's shape and test theories describing how space responds to mass and energy. Exploring the geometry of the cosmos reveals how deeply interconnected its components are. Matter, light, and space all contribute to the formation of structure, each influencing the others in subtle and powerful ways. The cosmic web emerges not only from the distribution of mass but also from the fabric of space itself. Through this understanding, the universe becomes a coherent system shaped by principles that operate consistently across all scales, revealing a cosmos unified by the underlying geometry guiding its evolution. Gravity governs the motions of galaxies and the growth of structure, yet its influence becomes even more striking when viewed across the full scale of the cosmic web. It acts as the organizing principle behind the patterns that fill the universe, guiding matter into coherent forms that persist across billions of years. Although gravity is familiar in everyday life, its role in shaping cosmic structure extends far beyond its terrestrial effects. Understanding how gravity behaves across vast distances helps explain the orderly arrangement of galaxies, clusters, and filaments observed today. At its core, gravity is the attraction between masses. In the context of the universe, this attraction determines how matter moves from the smallest scales to the largest structures. When regions of space contain more mass, they exert a stronger pull on surrounding matter. Over long periods, this pull draws material toward dense regions, amplifying small differences in density into large-scale structures. Galaxies, clusters, and filaments form where matter has accumulated through this steady inward movement. The resulting pattern reflects how gravity guides matter along paths dictated by the underlying distribution of mass. The influence of gravity depends on both the amount of mass present and the distance between objects. Although gravitational force weakens with distance, the enormous mass contained within clusters and filaments ensures that their influence extends across vast regions. Even sparse structures exert enough pull to guide the motion of galaxies and gas. Over cosmic timescales, these small but persistent influences accumulate, shaping the flow of matter throughout the cosmic web. In this way, gravity connects distant regions through subtle interactions that unfold gradually. The shape of the cosmic web reveals how gravity operates in a universe undergoing expansion. As space grows, matter moves apart unless gravity holds it together. This tension between expansion and gravitational attraction determines whether structures form or disperse. On small scales, gravity dominates, maintaining galaxies and clusters in stable configurations. On large scales, expansion becomes more influential, increasing the distance between structures. The balance between these effects creates a dynamic environment where matter gathers into dense regions while the space between them stretches. Gravity also influences how galaxies evolve internally. The orbits of stars within a galaxy depend on its total mass, including the unseen contribution of dark matter. This mass determines how stars move through the galaxy's gravitational field, shaping the overall structure. Spiral galaxies maintain their rotating disks and arms through a combination of rotation and gravitational attraction, while elliptical galaxies take on smoother shapes due to different histories of interaction and internal motion. In each case, gravity provides the framework that holds the system together. On larger scales, gravitational interactions between galaxies shape their paths through space. When galaxies pass near one another, tidal forces can distort their shapes and alter their internal structure. These interactions may draw out long streams of stars or compress gas to ignite new waves of star formation. Over long periods, repeated encounters can slow a galaxy's motion relative to its neighbors, eventually leading to mergers that reshape entire systems. Gravity ensures that these transformations follow consistent patterns determined by mass and distance. Clusters illustrate gravity's strength on even greater scales. The combined mass of many galaxies, along with hot gas and dark matter, creates a deep gravitational well that binds the cluster together. Galaxies move rapidly within this environment, yet they remain confined by the cluster's gravitational pull. The motions of these galaxies reveal the cluster's total mass, providing important clues about the dark matter that contributes most of its weight. By measuring these motions, astronomers infer how gravity shapes structures that span millions of light years. Gravity not only forms structure, but also allows astronomers to detect mass that cannot be seen directly. When light passes near a massive object, gravity bends its path, creating distortions known as gravitational lensing. These distortions reveal the presence and distribution of mass in regions that might otherwise remain hidden. Lensing maps help identify where dark matter is concentrated, offering a powerful tool for studying the invisible components of the cosmic web. Through its consistent influence, gravity shapes the universe with quiet precision. It guides matter toward dense regions, maintains the stability of galaxies and clusters, and reveals hidden structures through its effect on light. By understanding gravity's behavior across these scales, astronomers gain a clearer picture of how the cosmos formed and how it continues to evolve through processes that unfold steadily across immense periods of time. The universe not only contains visible structures such as galaxies and clusters, but also exhibits patterns in how matter moves through space over long periods. These large-scale motions reveal the gravitational landscape carved out by both ordinary matter and dark matter. By examining how galaxies drift in relation to one another, astronomers uncover details about regions of concentrated mass and the broader flows that guide cosmic evolution. These motions, though subtle, provide a deeper understanding of how the universe arranges itself across immense distances. Galaxies rarely remain fixed within the cosmic web. Instead, they move steadily under the influence of gravitational forces, pulling them toward regions of higher density. These movements often align with the filaments that form the backbone of the cosmic web. As galaxies drift along these elongated structures, they follow paths shaped by the underlying distribution of dark matter. This gradual flow reinforces the web's overall form, guiding matter toward intersections where clusters eventually grow. One of the most intriguing features revealed by studies of cosmic motion is the presence of large-scale flows converging toward massive concentrations of matter. These flows extend across vast regions, indicating that certain areas exert a stronger gravitational influence than others. By measuring how galaxies in different directions move relative to Earth, astronomers identify areas where matter has collected into exceptionally large structures. These regions help shape the motion of galaxies across hundreds of millions of light-years, revealing the scale at which gravitational effects operate. The study of galaxy motion is complicated by the simultaneous expansion of the universe. As space stretches, galaxies appear to move away from one another, even when no local gravitational interaction is present. To understand the true motion of galaxies, astronomers must separate this expansion from the internal movements caused by gravity. By analyzing deviations from the expected effects of expansion, scientists identify the influence of unseen structures guiding the flow of matter. These deviations map the gravitational contours of the universe, showing how matter responds to deeper forces. Measurements of cosmic flows also help identify areas where dark matter is concentrated. When galaxies move toward regions with no visible structure, it indicates the presence of mass that does not emit or absorb light. These observations strengthen the understanding that dark matter dominates the mass budget of the universe, shaping the large-scale distribution of matter. By tracing the motion of galaxies, astronomers build a dynamic map of this invisible component, revealing how it guides matter through space. Over long periods, these flows contribute to the growth of clusters and superclusters. As matter moves inward along filaments, it becomes part of increasingly dense regions. This slow movement is essential for maintaining the structure of the cosmic web. The inflow of material allows clusters to grow gradually, while the outflow of material into voids continues to deepen the contrast between different regions. The result is a large-scale pattern that reflects both the distribution of matter and the motion that continually reshapes it. The consistency of these flows provides valuable information about the forces governing the universe. If gravity operated differently on large scales, or if the geometry of space were significantly altered, the motions of galaxies would reflect those changes. Instead, observations show a coherent pattern that agrees with theoretical models based on general relativity and the presence of dark matter. These patterns offer strong support for the current understanding of how matter interacts with gravity, confirming predictions across a wide range of scales. Through studies of cosmic motion, astronomers gain a deeper appreciation for how movement shapes the universe. Galaxies trace paths carved by gravitational landscapes, responding to mass both near and far in ways that illuminate the structure of the cosmos. Their steady drift through space reveals the interconnected nature of cosmic architecture, showing how subtle forces acting across extraordinary distances guide matter into enduring patterns. This gradual, deliberate flow offers a clear window into the mechanisms shaping cosmic evolution, helping reveal how the universe forms and maintains its vast and intricate structure. The development of cosmic structures over time relies heavily on the exchange of matter and energy across different environments. This exchange occurs gently and steadily, shaping how galaxies form, how clusters grow, and how the large-scale arrangement of the universe evolves. Matter flows along gravitational paths, energy radiates outward from stars and hot gas, and the space between structures transforms as expansion continues. These processes unfold together, producing a cosmos that changes gradually while preserving the coherence of its overarching patterns. One of the key mechanisms driving cosmic evolution is the movement of gas between galaxies and the surrounding intergalactic medium. Gas flows inward along filaments, providing the raw material needed for star formation. As stars form, they heat and stir the surrounding gas, altering its temperature and density. When these stars eventually release energy and material, they enrich their environment with heavier elements. This continuous cycle of inflow, transformation, and release links the life of stars to the growth of entire galaxies, revealing how intertwined these processes are. Clusters demonstrate this connection on larger scales. As matter accumulates within their gravitational wells, galaxies interact with one another and with the hot gas filling the cluster. These interactions help regulate how gas circulates, preventing it from cooling too rapidly or collapsing into new stars. The balance between cooling and heating shapes the long-term development of clusters. Over immense stretches of time, gradual adjustments in temperature, density, and motion maintain the stability of these systems, allowing them to grow without losing coherence. Energy released by galaxies also influences their surroundings. Active galactic cores can emit streams of particles that heat nearby gas, altering its behavior. Stellar explosions distribute material across space, adding complexity to the chemical composition of large-scale structures. These energetic processes operate quietly across cosmic distances, contributing to the gradual evolution of the environment. The effects may not be noticeable on short timescales, but over billions of years they shape how matter accumulates and how new structures emerge. The connection between matter and energy becomes clear when examining how light travels through the cosmos. Light from distant galaxies carries information about the conditions present when it was emitted. As it moves across expanding space, its wavelength stretches, providing clues about the rate of expansion and the geometry of the universe. When light passes near massive structures, gravity bends its path, creating distortions that reveal the distribution of mass. These subtle shifts in light are essential tools for mapping the cosmic web, allowing astronomers to study regions that cannot be observed directly. The exchange of matter and energy also affects the behavior of voids. Although these regions contain little material, they expand more quickly than the denser surroundings. As gas and galaxies drift outward, voids become even emptier, deepening the contrast between sparse and dense regions. This expansion is reinforced by the inflow of matter into filaments and clusters. Together, these processes maintain the structure of the cosmic web, ensuring that its patterns persist across enormous distances and time periods. Despite the complexity of these interactions, the overall progression remains gentle. Changes occur so gradually that the cosmos appears calm and steady when observed at large scales. This steadiness mirrors the quiet rhythm of natural processes unfolding over immense periods. If your breathing has begun to slow or deepen while listening, that response aligns naturally with the calm pace of these cosmic transitions. The universe evolves through consistent, unhurried movement, offering a sense of ease reflected in its gradual shifts. Understanding how matter and energy flow across the cosmos provides insight into the long-term behavior of the universe. It shows how small interactions contribute to large structures, and how energy radiated by stars and galaxies influences the broader environment. These connections reveal a system governed by physical laws that remain reliable across time, guiding the development of the cosmic web and shaping the appearance of the universe as it continues to expand and transform. The universe's large-scale structure appears intricate, but its formation can be traced to a small number of fundamental physical principles operating consistently across time. One of these principles is the predictable behavior of matter under the influence of gravity. Another is the uniformity of the laws governing energy, motion, and radiation. Together, these principles create conditions that allow complex patterns to emerge gradually from simple origins, connecting events that occurred shortly after the earliest era to the vast structures visible across the sky today. A crucial aspect of cosmic evolution is the stability of physical laws. Measurements show that the interactions governing matter, light, and energy have remained consistent over billions of years. This stability allows small fluctuations in density to grow predictably, guiding matter toward regions where structures eventually form. Without this consistency, the universe might have developed unevenly or failed to produce coherent patterns. Instead, the same forces acting today shape the earlier stages of structure, ensuring continuity across cosmic time. The distribution of matter provides another key to understanding how complex patterns arise. In the early universe, slight variations in density created regions where matter accumulated more rapidly. These regions served as the seeds of galaxies, clusters, and filaments. As matter collected, gravitational attraction increased, reinforcing the initial differences. This feedback mechanism allowed small fluctuations to grow into the large-scale arrangement of the cosmos. Observations confirm that these early variations align closely with the structures visible today, demonstrating how deeply interconnected these stages are. Cosmic expansion also contributes to the formation of structure. As the universe grows, matter spreads out, creating opportunities for gravitational effects to strengthen local patterns. Expansion does not erase the differences created by early fluctuations. Instead, it stretches space in a way that enhances the contrast between regions of higher and lower density. Over time, this contrast becomes more pronounced, allowing voids to form and clusters to grow. The combined influence of expansion and gravity shapes the overall appearance of the cosmic web. Radiation plays a significant role as well. In the early universe, radiation exerted pressure on matter, resisting collapse. As the universe cooled, this pressure weakened, allowing gravity to take over more effectively. The transition from radiation-dominated behavior to matter-dominated behavior marked a turning point in cosmic evolution. This shift allowed fluctuations to grow more rapidly, setting the stage for the formation of galaxies and other structures. The interplay between radiation and matter continues to influence behavior on smaller scales, guiding how gas cools, collapses, and forms stars. The influence of dark matter is essential in this process. Its gravitational pull shapes the framework upon which ordinary matter gathers. Because dark matter interacts only through gravity, it began forming the first structures earlier than ordinary matter. These early concentrations served as anchors that guided the flow of gas and provided the scaffolding needed for galaxies to form. Without dark matter, the universe would lack the coherent patterns observed today. The behavior of galaxies, clusters, and the cosmic web all depend on dark matter's presence. Dark energy adds another important element by controlling the pace of cosmic expansion. As expansion accelerates, distances between structures increase, allowing the universe to maintain its overall shape while still permitting matter to gather in local regions. This acceleration influences the rate at which structures form and how they evolve. Over long periods, dark energy shapes the boundaries of cosmic regions, influencing how matter flows and how the cosmic web stretches across space. These principles, gravity, expansion, radiation, and the properties of matter and energy, work together to create a universe that evolves steadily and coherently. Each contributes to the formation and maintenance of structure, guiding matter into patterns that reflect the early conditions of the cosmos. As astronomers study these patterns, they uncover new details about how the universe behaves on all scales, deepening the understanding of its long-term development. The existence of these large-scale structures highlights the remarkable ability of simple physical laws to produce complexity. From faint fluctuations in the earliest periods to the vast cosmic web spanning billions of light-years, the universe grows through consistent processes acting across time. By tracing these processes, scientists gain insight into how the cosmos reached its current form and how it will continue to evolve through the enduring influence of gravity, expansion, and the interplay of matter and energy. The cosmic web's intricate structure reveals how patterns of matter extend across unimaginable distances, yet these large formations are composed of countless smaller interactions unfolding gradually over time. Each filament, cluster, and void reflects the accumulation of many subtle processes guided by gravity, expansion, and the reliable behavior of matter and energy. As astronomers examine these structures more closely, They uncover the quiet mechanisms that have shaped the universe's appearance from its earliest stages to the present. One of the notable features of the cosmic web is the coherence of its filaments. These elongated structures span hundreds of millions of light years, yet they form through the steady movement of matter responding to gravitational gradients. Gas and galaxies drift slowly along these paths, guided by the distribution of dark matter. Although this movement occurs across immense scales, it proceeds with steady predictability, reflecting the consistent influence of gravity. Over time, the accumulation of matter reinforces the shape of the filaments, allowing them to remain stable even as the universe expands. Clusters form where filaments intersect, creating regions of higher density. These intersections become centers of strong gravitational attraction, drawing in additional material from surrounding space. As galaxies gather within these clusters, their interactions generate heating, turbulence, and gradual structural changes. The movement of galaxies within a cluster may appear chaotic over short timescales, yet when observed collectively, their behavior follows clear patterns shaped by the gravitational environment. This organized motion reveals the deep connection between individual systems and the larger structures they inhabit. Voids present a contrasting environment. These expansive regions contain very little matter, yet they play a significant role in shaping the cosmic web. As matter flows out of voids and into surrounding filaments and clusters, the boundaries between regions sharpen. The expansion of space acts more strongly within voids, accelerating their growth relative to denser regions. This gradual divergence enhances the contrast across the cosmic web, creating a landscape characterized by delicate balance between dense structures and the vast emptiness around them. The transitions between these regions illustrate how smoothly the universe evolves. Matter does not move abruptly from one environment to another. Instead, it flows gently along gravitational contours, adjusting gradually to changes in density and curvature. These subtle adjustments accumulate over billions of years, producing the elaborate patterns visible in cosmic surveys. The large-scale structure of the universe emerges not from sudden events but from the steady influence of predictable forces shaping matter over immense spans of time. Dark matter plays a central role in maintaining this coherence. Its distribution defines the gravitational framework of the cosmic web, determining where structures form and how matter moves. Even though it cannot be observed directly, its influence becomes clear when examining the motions of galaxies or the bending of light through gravitational lensing. These observations reveal the underlying structure that guides the visible universe, showing how dark matter provides the foundation upon which baryonic matter arranges itself. Dark energy contributes to the long-term evolution of these structures by influencing the overall expansion of space. As expansion accelerates, the distances between clusters and filaments gradually increase. However, the internal stability of these structures remains intact due to the strength of gravitational attraction within them. This balance allows the cosmic web to maintain its form even as the universe grows larger. Over time, expansion emphasizes the differences between regions, stretching space while preserving the coherence of local environments. The combined effects of gravity, dark matter, dark energy, and the behavior of baryonic matter create a universe that evolves in a calm, steady manner. Nothing unfolds abruptly on these scales. Instead, the cosmos changes through slow, deliberate processes that reflect deep physical laws. If you sense your breathing becoming slower or more settled while considering these vast interactions, that response aligns naturally with the unhurried rhythm of cosmic evolution. The universe itself moves at a pace that encourages stillness, with each structure growing through gradual, predictable motion. Exploring these patterns reveals how the universe balances expansion with the formation of structure. The cosmic web stretches outward while maintaining the integrity of its filaments and clusters. This balance illustrates the interplay of forces guiding the cosmos, shaping matter into forms that persist across billions of years. By studying these structures, astronomers gain insight into the underlying principles that govern the universe, revealing a coherent and interconnected system evolving with remarkable consistency. The structure of the universe can also be explored through the distribution of temperatures across different cosmic environments. Temperature variations provide valuable information about the physical processes shaping matter on both small and large scales. These variations arise from interactions between gas, radiation, gravity, and the expansion of space. By examining how temperature changes across the cosmic web, astronomers gain insight into how energy flows through the universe and how matter responds to shifts in its surroundings. In clusters, temperatures reach some of the highest values found outside of stars. The gas within these regions is heated by the motions of galaxies, the effects of gravitational compression, and energetic events, such as stellar explosions or activity from galactic cores. This hot gas emits radiation detectable in the X-ray portion of the spectrum, allowing scientists to map the distribution of temperature within the cluster. These temperature maps reveal how gas circulates and how gravitational forces shape the internal structure of the cluster, offering a detailed view of processes that occur over immense periods. Filaments represent a different thermal environment. The gas flowing along these elongated structures is often warm or mildly hot, heated by the gradual collapse of matter and the effects of shock waves forming as gas adjusts to changing gravitational conditions. Although this gas is less energetic than the material in clusters, it still holds important clues about how matter moves through the cosmic web. Temperature variations along filaments help reveal where matter is gathering most rapidly and how flows evolve as gravitational forces adjust. Voids, by contrast, contain cooler and more diffuse gas. This gas expands along with space, reducing its temperature over time. The low density within voids slows interactions between particles, allowing the gas to cool gradually as radiation escapes more easily. Although voids may appear empty, their temperature patterns provide information about how expansion influences matter in regions where gravitational forces are weaker. These cooler environments contrast sharply with the hotter regions of clusters, highlighting the diversity of physical conditions across the universe. The interplay between heating and cooling shapes much of the universe's thermal behavior. Cooling processes occur when gas radiates energy into space, gradually lowering its temperature. This cooling allows gas to collapse more efficiently, promoting the formation of stars and galaxies. Heating processes, on the other hand, can oppose collapse by raising the temperature of gas, increasing pressure, and preventing it from condensing. The balance between these two effects determines how quickly structures form and how they evolve over long periods. Temperature also plays a significant role in determining the chemical composition of cosmic structures. Hot gas can cause atoms to lose electrons, creating ions that emit light at specific wavelengths. By studying this emission, astronomers identify the elements present and learn how they are distributed throughout clusters and filaments. Cooler gas allows molecules to form, contributing to the complexity of interstellar clouds where stars eventually take shape. These chemical transitions depend on temperature, linking thermal conditions to the development of galaxies and the environments within them. The early universe displayed temperature variations that later influenced the structure of the cosmic web. Small differences in temperature caused slight fluctuations in density, generating the seeds of future structure. These fluctuations, recorded in the cosmic microwave background, show how the earliest temperature patterns guided the growth of matter into the filaments and clusters visible today. By studying these temperature variations, scientists trace the connection between the universe's initial conditions and its current arrangement. As the universe expands, temperature continues to play a role in shaping its evolution. The cooling of space allows matter to settle into structures, while the heating from stars and energetic events redistributes energy across large distances. This dynamic balance ensures that thermal processes remain an essential part of cosmic evolution. Over billions of years, temperature variations smooth out or intensify depending on local conditions, revealing insights into the long-term behavior of the cosmic web. Examining temperature across the universe provides a deeper understanding of how matter and energy interact on large scales. It highlights the diversity of environments within the cosmic web and shows how local processes contribute to the broader structure of the cosmos. Through these observations, astronomers piece together the thermal history of the universe, uncovering the patterns that define its growth and the physical laws that guide its ever-changing form. Observing the universe across different wavelengths provides another layer of understanding about its structure and evolution. Each wavelength reveals a distinct component of cosmic behavior, from the distribution of stars and galaxies to the presence of hot gas, cold molecular clouds, and energetic processes occurring near black holes. By examining the cosmos through multiple forms of light, astronomers gather complementary information that deepens their understanding of how structures form, interact, and transform over time. Visible light shows the stars that populate galaxies, outlining their shapes and providing clues about their ages and compositions. Young, hot stars emit light that appears blue, while older, cooler stars emit a warmer glow. By mapping these colors across galaxies, astronomers determine how star formation varies within different regions. This information helps explain why some galaxies maintain well-defined spiral arms, while others appear smoother or more irregular. Visible light offers a detailed window into stellar populations, revealing how galaxies grow from the inside outward. Infrared observations reveal structures hidden from view in visible light. Dust absorbs and scatters short wavelengths, obscuring regions where stars are forming. Infrared light passes through this dust, exposing dense clouds where new stars emerge. These observations show how gas collapses into compact regions and how young stars heat their surroundings. They also reveal the distribution of dust within galaxies, providing insight into how material cycles from stars into interstellar space and back again. Infrared observations link the hidden process of star formation to the larger structure of galaxies. Ultraviolet light highlights energetic activity. Hot stars, active galactic nuclei, and regions of intense star formation emit strongly in this part of the spectrum. Observing these wavelengths helps astronomers identify where energetic processes are concentrated and how they influence the surrounding environment. Ultraviolet light reveals the presence of ionized gas, showing how stellar winds, radiation, and explosive events shape the interstellar medium. These observations deepen the understanding of how energy moves through galaxies and how it affects the formation of future generations of stars. X-ray observations expose the hottest environments in the cosmos. Gas in clusters reaches temperatures of millions of degrees, emitting strongly in X-rays. This emission outlines the distribution of mass within clusters, revealing where gas collects and how it circulates. X-rays also uncover energetic events near black holes, showing how material heats as it falls inward and how this heating influences the surrounding space. These observations provide a view of processes occurring in extreme conditions, offering insight into how matter behaves when subjected to intense gravitational and thermal forces. Radio waves reveal some of the largest and most diffuse structures in the universe. Neutral hydrogen gas emits radio signals that allow astronomers to map its distribution across galaxies and intergalactic space. Radio observations show how gas moves through the cosmic web, tracing flows that carry matter into galaxies and clusters. They also reveal the presence of jets emitted by active galactic nuclei, which can stretch across hundreds of thousands of light years. These jets influence the motion and temperature of surrounding gas, shaping the evolution of large-scale structures. The combination of observations across all wavelengths provides a comprehensive view of the universe. Each form of light reveals a different aspect, and together they form a cohesive picture of cosmic behavior. By comparing observations, astronomers connect the motions of galaxies to the heating and cooling of gas, the birth of stars, and the growth of massive structures. This multi-wavelength approach shows how various components work together, creating a dynamic environment shaped by intertwined processes unfolding over immense spans of time. These observations also reveal how the universe changes across different eras. Distant galaxies appear as they were billions of years ago, showing earlier stages of structure formation. Light from these galaxies has traveled through expanding space, carrying information about conditions that shaped their development. By observing the universe at many wavelengths and distances, astronomers build a timeline of cosmic evolution, revealing how structures emerged from early patterns and grew into the complex web visible today. Through this layered view, the cosmos becomes clearer. The interplay between stars, gas, dust, gravity, radiation, and expansion emerges from observations spanning the entire electromagnetic spectrum. Each wavelength contributes its own piece to the puzzle, revealing a universe woven from processes that operate consistently across space and time. By studying light in all its forms, scientists uncover the deep connections that shape the structure of the cosmos. The universe's structure can also be understood by examining how matter interacts with time itself. Time is not a separate backdrop against which cosmic events unfold, but part of the same fabric as space. Together, they form the setting in which gravity operates and in which matter evolves from one moment to the next. By studying how physical processes change across billions of years, astronomers gain insight into the long-term development of galaxies, clusters, and the cosmic web. Time plays a central role in determining the pace at which structures form. Shortly after the earliest period, matter in the universe was nearly uniform, with only slight variations in density. As time progressed, gravity amplified these variations, drawing material toward regions of higher density. This gradual accumulation of matter produced the earliest galaxies, which merged and grew into the large systems observed today. Without the steady passage of time, these small fluctuations would never have developed into the filaments and clusters that now span the universe. The formation of stars also reveals how time shapes cosmic structure. Stars emerge from dense clouds of gas that collapse under their own weight. The collapse process takes millions of years, and the resulting stars live for periods ranging from a few million to many billions of years. During their lifetimes, stars release energy that influences the surrounding gas, creating waves, heating regions, and altering future star formation. As stars reach the end of their lives, they return material to space, enriching the environment for later generations. This ongoing cycle, unfolding over long spans of time, plays a major role in shaping the chemical and structural evolution of galaxies. Galaxies themselves change significantly over time. Early galaxies tended to be smaller and more irregular, containing young stars and abundant gas. As time passed, these galaxies merged, forming larger systems with more complex structures. Modern galaxies show evidence of these mergers in their shapes, colors, and internal motions. Spiral patterns, smooth ellipses, and irregular arrangements all reflect the cumulative influence of past events. These changes illustrate how the universe's appearance depends on processes that unfold steadily across millions or billions of years. The behavior of clusters also evolves over time. In the early universe, matter had not yet gathered into the large concentrations observed today. As time progressed, galaxies drifted toward dense regions, slowly building the clusters that now contain thousands of galaxies. These clusters continue to grow as matter flows inward along filaments. The temperature, density, and distribution of gas within clusters adjust gradually as gravitational forces, stellar activity, and gas motions interact. These changes reveal how time allows small effects to accumulate into large, coherent structures. On even larger scales, the cosmic web itself changes. Although its overall form remains recognizable, the distances between structures increase as the universe expands. Filaments become more stretched, and voids grow larger, yet the internal coherence of dense regions remains, supported by gravity. These shifts occur so gradually that the cosmic web appears stable across human timescales, but when viewed over billions of years, the changes become significant. Expansion ensures that cosmic structure is dynamic, even if it appears static when observed from a single moment. Time also influences the behavior of light. As the universe expands, light traveling from distant galaxies stretches, shifting toward longer wavelengths. This effect, known as redshift, allows astronomers to determine how far light has traveled and how the universe has changed during that journey. Redshift measurements reveal not only the distances to galaxies but also how fast the universe was expanding when the light was emitted. By combining these measurements across many objects, astronomers build a timeline of cosmic evolution. The interplay between matter and time highlights the universe's gradual, evolving nature. Nothing changes suddenly on cosmic scales. Instead, structure emerges through processes that unfold at predictable rates. As matter drifts, collapses, or expands, the passage of time allows these processes to accumulate, shaping the appearance of the cosmos. Even the calm patterns observed in today's sky are the result of countless events unfolding in sequence over vast periods. Understanding how time influences cosmic structure provides a deeper appreciation of the universe's evolution. It shows how everything observed today is part of a long continuum extending back to the earliest moments. Through this perspective, the cosmos becomes a living system shaped by the gentle interplay of matter, gravity, expansion, and the steady passage of time. The structure of the cosmos, vast and intricate as it appears, reveals a universe shaped by steady, predictable principles, acting across extraordinary spans of time. As scientists study these structures, they uncover a remarkable consistency in how matter gathers, how energy moves through space, and how the fabric of the universe adjusts to the interplay of gravity and expansion. This consistency allows galaxies, clusters, filaments, and voids to develop their characteristic forms, each shaped by processes that unfold gradually yet persistently across billions of years. When examining the universe on its largest scales, a sense of coherence emerges. The cosmic web stretches across space with a pattern that reflects the earliest fluctuations imprinted shortly after the universe began. These faint variations grew slowly, guided by gravity and influenced by the presence of dark matter. Over time, small differences in density became enormous structures that now define the architecture of the cosmos. The shape of the universe today is the visible expression of these early patterns interacting with the laws of physics in a calm and continuous way. Galaxies occupy a central role in this structure, serving as the primary sites where stars form and evolve. Each galaxy contains its own internal history, shaped by the movement of gas, the birth and death of stars, and the long influence of gravitational interactions with neighboring systems. These internal processes operate alongside the broader movements that guide galaxies through the cosmic web. The combined effects create systems that are complex yet governed by reliable rules, allowing astronomers to trace their evolution across time. The delicate balance between expansion and gravity adds depth to this story. Expansion increases the distances between structures, gradually stretching the cosmic web while preserving its overall form. Gravity counteracts this stretching in dense regions, maintaining the cohesion of galaxies, groups, and clusters. This balance enables the universe to grow while retaining familiar patterns, illustrating how different forces cooperate to produce a stable yet evolving environment. Over the course of billions of years, the boundaries between dense and sparse regions sharpen, revealing clearer outlines of the cosmic web. Light provides the means to explore these structures. As it travels across expanding space, it carries information about galaxies as they once were, showing earlier stages of cosmic evolution. Observations of distant light allow astronomers to reconstruct how the universe changed over time, revealing both the growth of structure and the expansion of space itself. The bending of light around massive regions helps map the distribution of dark matter, uncovering the invisible framework guiding the universe's large-scale behavior. Through these observations, a consistent picture emerges, connecting distant ages to the present moment. The processes shaping the cosmos unfold so gradually that they mirror a natural sense of calm. Expansion progresses smoothly, galaxies drift along gravitational paths at steady rates, and the growth of structure occurs through the accumulation of countless small adjustments. If you feel your breathing becoming slower and your thoughts settling as you listen, that response aligns gently with the unhurried rhythm of the universe itself. The cosmos evolves at a pace that invites rest, offering a sense of ease through its quiet, predictable motion. Understanding the structure of the cosmos brings together many layers of physical law, from the behavior of individual particles to the arrangement of the largest formations in the universe. Each component contributes to a coherent whole, shaped by gravity, energy, expansion, and time. The result is a universe that appears immense yet remarkably ordered, evolving through processes that remain consistent even as they generate extraordinary diversity. By studying these structures, astronomers learn not only about the cosmos but also about the timeless principles guiding its development. As the final patterns of this story come into view, the universe reveals itself as both dynamic and serene. Its vast structures grow through steady motion, and its deepest forces act with quiet reliability. This perspective offers a gentle space for rest, inviting the mind to settle into the same calm continuity that guides the cosmos. We from Sleepy Stories wish you a good night.